Uh, in the yesterday's session, we have already talked about heap and what are the properties of the heap and as the two main properties. Yes, one was the shape property and the other one was the parent dominance property. So we have already talked about the heap construction algorithm yesterday, and as we have already told, heap construction involve two kind of methods. The first one is the bottom up approach and the second one is the top down approach. So previously we have talked about the bottom up approach. We have seen the algorithm as well as two programs. So now let's quickly, before we move on to top down approach, let's quickly check what is the uh, time complexity of this algorithm. So let me share with you the document here. So as you can see here, uh, in this, it says that if it is a complete tree and in the worst case, every time when you have a particular algorithm, let's say I have 2 here and I have 5 here, I have 4 here and I have 6 here and 3 here and I have 7 here. Yes, so in this case, as you can see it on the board, that the first element is 2, then 5, and then 7. Yes, because out of these two child nodes, 5 is greater, so it will be moved up and this will come down. And then, so in that case, every time what you need to do is you need to actually traverse through the complete tree. Yes, so if you have a complete tree and in the worst case, every time that you have to check whether a key is at its proper place, you have to traverse or make a comparison at each level. Yes, so in that case, we will talk about the worst case efficiency of the algorithm. So for that, uh, as we have checked in the algorithm, we had two iterative loops. Yes, the first for loop, that is for all the elements or the parental nodes, that is from I, that goes from 0 to n by 2 minus 1. Then we have another while loop that goes for all the adjacent nodes. Now for the two, we have these summation values, and within the while loop, we have two if conditions, and those if conditions were to check one, to find whether a particular node is greater or it has a sibling which is of higher value. Yes, the another one was to check whichever node is higher with the parent node. So we need two comparison at all time. So that's why 2 is here. And how many number of comparisons that you would need to do is h minus I. So at any ith level, when we are talking about for any ith level, if h is the complete height, so the number of comparisons that you have to do would be always h minus I. Yes, so that is why you have here 2 into h minus I, and we have these two summation series. So this is the worst case time complexity. On solving this, what we get here is 2 into n minus log of n plus 1. So if you have any equation like this, so in this case, the highest polynomial factor here is 9. So what we say here is that the bottom up approach is governed by n. Okay, 2n, or what we can simply say it is n. So that means for n number of elements, the bottom up approach will have a time complexity governed by the factor of n. Yes, so now let's check with the top down approach. So I hope the bottom up approach is clear. So let me now take you to the top down approach. So the top down approach is including one basic thing, that every time when a new element comes, we allow the element to insert at the last vacant place or the next index, and then we heapify or place that particular key at its proper place. Yes, so let's quickly take the example, whatever is given in your book that we have already done yesterday. Yes, so we had 9, 6, 8, and then 2, 5, and 7. So this particular node was empty. Let's say we need to insert the element 10 into this particular heap, and we need to, as we know that 10 is the element which is greater than all the other heap elements. So definitely it has to come to the root of the tree. So first what we will do is we'll keep this 10 at the next vacant position. Yes, so this was index 1, 2, 3, 4, 5, 6, and 7. So at the index 7, we have included 10. Now, once we have included this, we will be comparing this with its parent node. So once we compare it with the parent node here, we know 8 is lesser than 10. So the parent dominance property is not followed. So we will swap the two values and it will result into a tree heap that will look like this. At this position, when 10 have reached here, so we will keep on iterating or keep on recursively doing the same thing. That means checking the node value with its parent node, and we will only stop if we have reached either the root of the heap or the parent node value is greater. Yes, so right now here also we are going to compare it with the parent node. So the parent node value is greater. So what we are going to do is we are going to swap the values again. So this will result into so 10 have been inserted into the heap and it has reached its proper position. So that is how your top-down approach works. Now, comparing this approach with your bottom-up approach, we earlier said the bottom-up approach is taking it's of the time complexity n, whereas this one, it is going to have maximum how many number of comparison? One comparison at each level. Maximum what it has to do is from the leaf node, it will be moving up and going to the root. And that is equal to the height of the tree, which is of the order of log of n. So definitely the top-down approach is much better than your bottom-up approach. But this approach is not used that very frequently because most of the time when we are working with this, we are already have those set of elements. Yes, and it is better to use a bottom-up approach. Okay, so next we move on to how do we do the deletion from this. Let's say we are given one particular heap and we want to delete an element from the heap. So let's quickly check that also. I hope the top-down approach is completely clear, or do you want me to take the example that we have taken in the last session from the previous year question papers? Please let me know if you want to include the example here.
Yes, ma'am.
Okay, sure. Okay, so this is the example that we have taken yesterday, which have 1863574. So if you have to construct a heap using the top down approach, so in that case you will first have the element 1. So right now what we do is we take an empty array h. If this was h, let us take it as h1. So at index 0 we are going to assume that h0 is not used, and at index 1 we include the element 1 because this element is at the root, so it will not do any other kind of processing. So the next index value we will include 8, and then we will compare it with the parent node value if the parent dominance property is satisfied. So in this case it is not satisfied, so it will result into this kind of a tree. Yes, so this will be changed to 8 and this is made equal to 1. So the next element, so we have first included 1, then we have included 8. Now we are going to include 6. So 8 is here, 1 is here, and 6 is here. So 6 will be compared with 8, its parent node, and it follows the parent dominance property. So nothing is changed, and it is at this level only because it is when it is compared here, it has actually reached the parent node also. So after that, we will insert 3. So for that, it will be 8, 1, 6, and 3. So 3 will be compared with its parent node value. So that is a greater value. So it will be swapped. So this will result into 8, 3, 1, and 6. At this point, it is again compared with its parent node value because it has not reached the root node. So this follows the parent dominance property. So nothing will be changed. So now this array is changed to 8, 3, 6, 1. So the next element that we are going to add is 5. So for that, 8, 3, 6, 1, and 5. So again, it is compared with its parent node value. Parent node value is 3. It doesn't follow the parent dominance property. So this will be changed to 8, 5, 1, 3, and 6. So in this case, what it is doing is it is only comparing here, okay, and from here it again compares with its parent node, and here it follows the parent dominance because 8 is greater than 5, so it will stop here. So next what we are getting here is 8, 5, 6, 1, 3. So the next element to be inserted is 7. That will be 8, 5, 6, 1, 3, and 7. So again, it will be compared with its parent node. So it will result into another heap 8, 5, 7, 1, 3, and 6. Again, this will be compared with its parent node. It follows the parent dominance property. So nothing is changed. So it stops there. And then next we have to insert 4, the last element. So it will be 8, 5, 7, 1, 3, 6, and 4. So 4 will be compared with its parent node. It follows the parent dominance property. So it will stop here. So this will be the final heap that you will get using the top-down approach. And the values here will be 8, 5, 7, 1, 3, 6, 4 into the array. So this is the input that is given and this is the output. I hope that is clear. Yes. So let's move on to how we work with the deletion from a heap. So for deletion, right now we are assuming that the key deletion is from the top of the heap. So let's take the same heap that we have constructed right now. So let me draw this again. So the heap that we get here is 8, 5, 7, 1, 3, 6, 4. So the deletion from a heap works in 3 steps, where the step 1, what it says is that exchange the root key with the last key of the heap. That means these two will be exchanged. Fine. So exchange between last key and the root key. So your whatever is your root key, that will be placed at the last, and the last key will be placed at the root. So this will be made as 4 and this will be made as 8. Fine. So next step is decrease the heap size. That means from n it will be changed to n minus 1 number of elements. So this will be taken out. So what you have gotten is the element or deletion from the heap. We wanted to delete it from the root, yes, because 8 was here. So if we have directly deleted it, it would have not been possible to actually arrange the elements properly. So what we do is we shift the root element to the last and the last element to the root and then take out the last element. So we have deleted this. But what has happened here is now it doesn't follow the second property of heap. Okay, is the board clear now? What I'm writing, if it is not clear, okay, I'll repeat it, okay, so that you can follow through that. So what I have told is decrease deletion from the heap have 3 steps. Step 1, what it says is exchange the last key with the root key, and after that decrease the heap size from n to n minus 1. So earlier in this heap you have 7 elements. So right now it will be 6 element and the nth element or the 7th element is taken out. So that is the top of the heap that we have taken out. Fine. So once this is done, then the next step is to heapify the remaining set of elements. And in that case, what happens is we shift down. So this becomes the key value and we shift this key value down into the heap using the bottom up heap construction. Yes, because the heap is already there. So we cannot use the top down approach. So what we are going to use is the bottom up approach. I hope till this point it is clear. Yes. So if we have to use a bottom up approach for this, we will start from this node. Yes, we'll check whether its parent node have the parent dominance property or not. So it has. For this node, it has. For this node, it has. Then we check with this 7 with 4. Yes. So in that case, what we will do is we will check whichever sibling is higher and then we will put that here and it will be this here. So now once we want to put it here, again it will check with the child node. So this value is not there. So 6 will come here and 4 will go. So that is how your algorithm is going to work. Okay, I'm going to unmute you all. Let me know if the session is clear or not. Okay, so moving back to where we were. So what we have already told is deletion of the elements. Yes, it is a three-step process. So what does it do is it will swap the first element with the last one and take out the last, and then it will allow the first element to move to its proper place. So that is how the algorithm will work. So in this case, when we are actually only swapping the two elements, it will take, we say it is a constant time. When we delete element, the last element, it is also the constant time. Only when we are working with the third step, that is EP5, where the key element at the root that is taken is placed at its proper place, and the heap properties are made sure that they are uh, um, being taken care. So in that case, it is only the bottom up approach. Okay. So, and in that case, the other for loop is not going to work. It is going to only work for a single level. Yes, because we are only considering the element that is at the root. So it is going to be not more than big O of log of n. Yes, so if you remember the earlier for the bottom up approach, we got something like this is equal to 2n minus log of n plus 1. Yes, so in that case, we are actually considering something from here. We are not taking the n, but it is going to be big O of log of n. Yes, so deletion is going to take big O of log of n. So once this is the working of heaps. Now let's move on to what is heap sort. So when you are given certain set of elements and you want to sort those elements using the heap, yes. So in that case, we use the heap sort. So for sort, it works in two stages. So let's see what are those two stages. So the stage one is when we have to do the construction of the heap. We call it as heap construction. So let me take the same one here, what we had, so that we can work with the same. See, if we had this array elements given to be sorted, we construct a heap using that. So we get 8, 5, 7, 1, 3, 6, 4. So the heap construction is done here. Yes, so that is the stage one. Stage two, if you can see here, at every point, what we are going to delete is the highest elements. So in the second step, we do maximum deletions. That means we will select the root node and apply the deletion. So apply root deletions till you are left with only a single element or for the complete n minus 1 heap. Yes, so we'll keep on applying the root deletion. So first 8 is taken out, then 7, then 5, then 6, and 4, 3, 1. So the deletions will happen in that order. Yes, so let's quickly see, because every time when the deletion is there, it is going to work in 3 steps. That means it is going to exchange root and the last element, decrease the heap, and then heapify. Fine. So what we are going to do is, we have known how the heap construction is done. We have checked this in the previous session. Now from the same heap, we are going to do the deletions and get a sorted array. So let's quickly see that. Okay. So from this tree, again, we have to swap the 2. So 4 comes here, 8 comes here. So from this step, we are going to get 8. Yes. So let's say my sorted array is this. So at the first index, 8 have come because it is deleted and it is kept here. Now we will do the heapify of this one. So it will be 7, 5, 6, 1, 3, and 4. So again, at the second step, so this was the first deletion. This is the second deletion. So what again it is going to do is exchange these two. Yes. So it will become 4, 5, 6, 1, 3, and 7. So it's going to delete this. So at the second index, you get 7. And again, from here, it is going to heapify the remaining elements. So from here, whichever is the greater child node, that will be swapped with 4. Yes. After that, at the next step, with the last element, it will be exchanged. So 3 will come at the root, then 5, 4, and 1, and 6. And we will delete 6 and keep it into the next index of the array. So once this is done, again heapify this. So out of the 2 child nodes, 5 is greater. So 5 will come here, 3 will come here, 4 will come here, and 1 will come here. 3 and 1, it will not do anything because 3 is following the parent dominance. If there would have been a greater value here, so we would want to follow the parent dominance. So it will work with the bottom up approach. So from here, again, what we are going to do is the first and the last. So this will come as 1, 3, 4, and 5, and it is deleted from here and it is kept at the next index, and remaining elements we need to heapify. 3 and 4, 4 is greater, so 4 will be at the root. This is 3 and this is 1. Again at this stage, it is going to swap these two. So 1 will come here, 3 is here, and 4, which is deleted. So it is kept at the next index, and you are remaining with 1 and 3. Again heapify this because it doesn't follow the parent dominance. So 3 will come here, 1 will come here. Again it will exchange. If you see here, it is again exchanging here. It will be, it will be 1 and then 3, and this 3 is taken out and kept at the next index. And then you are left with a single element which is kept at the last. So what we have got here is sorted elements. So if you are saying that you have the maximum element at the root of the heap, you will get the elements in the decreasing order. If your heap is made such that the root element is the smallest element, in that case you will get a increasing order. Yes. So any doubts for this? So that is all for heaps. In that we have done with the heap construction, taken the two approaches, bottom up approach and the top down approach. Then we have checked with deletions and heap sort. It takes both the two. At the first step, it will use the heap construction, and at the second step, it will use the deletion from the heap to get the sorted elements from the heap. Yes, students, any doubt till here? I hope it is clear. Okay. Uh, you guys can let me know in the chat that what all is not clear so I can repeat that. So shall I assume that this is all clear to you?